We're going to begin our discussion of chemical reactions and what that actually entails. So this entire next series of videos will cover exclusively chemical reactions. Now, ultimately, what we're going to talk about is the Ionic theory of solutions and the solubility rules. So what happens when we actually put two solutions together? Will they form some sort of precipitate? Will they have a reaction? We'll also talk about molecular and ionic equations. And then we'll move into precipitation reactions. And then two of the most biologically important reactions, those concerning acid-base reactions and then oxidation-reduction reactions. And we'll see how to balance those simple oxidation-reduction reactions. And lastly, we'll end with molar concentrations, diluting solutions, and then a very, very important laboratory skill, which is known as volumetric analysis. But let's start by talking about what chemical reactions actually are. Chemical reactions are the heart of chemistry. Some reactions, such as those that accompany a forest fire or the explosion of dynamite, those are pretty dramatic. Others, much less obvious, although all chemical reactions must involve detectable change, because a chemical reaction involves a change from reactant substances to product substances, and then ultimately the product substances will have different physical and chemical properties from those of the reactants. So in this chapter we're going to talk about the major types of chemical reactions, including precipitation reactions. So precipitation reactions. And chemists have a tendency to be a little bit lazy. They don't like to write out the whole entire word reactions, so RX and S suffices for reactions. But we're going to talk about precipitation reactions, and then we'll talk more about some of the most important reactions which involve ions in solution or in water. And we'll take a look first at these ions and see how we can represent them through chemical equations, and then the reactions that are involving those ions in aqueous solution. Some of the questions that we are going to answer throughout the course of this next section is, what is the evidence for ions in solution, or how do we write chemical equations for the reactions involving those ions, and how can we classify and describe the many reactions we observe so that we begin to understand them. And lastly, what is the quantitative description of solutions and the reactions in those solutions? But in order to do that, we need to talk about the Ionic theory of solutions. So we have this Ionic theory of solutions. And solubility rules. So, will something be a precipitate if the reaction goes forward, and how can we determine that? So solubility rules is what we'll discuss towards the end of this section. But chemists began to study the electrical behavior of substances in the early 19th century, and they knew that you could make pure water electrically conductive by dissolving certain substances in it. In 1884, a chemist by the name of Svante Arrhenius proposed the Ionic theory of solutions to account for this conductivity. He said that certain substances produce freely moving ions. So certain substances produce freely moving ions. When they are dissolved in water. And these ions are the thing that is actually conducting an electrical current. So, for instance, we saw that when we took sodium chloride, which is an ionic substance, we said that sodium chloride is actually a mixture, is an ionic compound that is actually composed of sodium ions and chlorine ions. Now what we did was we took a beaker or a small container which had some distilled water in it, and then we dropped in sodium chloride. So once we put sodium chloride in, we had a voltmeter. And we tested to see how much current was actually being produced. If it was different from just regular old distilled water, and what happened when we actually put that in. We saw that when we put in sodium chloride, the resistance actually dropped, which means that there was more current passing through that solution. So the resistance went down because the sodium and the chlorine ions were actually able to move back and forth. Now, in this example, we had a minus sign and a plus sign, or a minus charge and a positive charge, just like you would have in a normal battery. And on this negatively charged wire, the positively charged sodium ions began to gravitate towards this negatively charged wire. Conversely, on the other side, this positively charged wire, we had chlorine ions which were moving, or which are attracted to that. It is that movement towards these particular electrodes that causes that current. So what we do is we can classify these types of solutions as two different types. One is an electrolyte, or an electrolytic solution. So we have electrolytes and non-electrolytes. There, got it all fit. So we have electrolytes and we have non-electrolytes. So that is the division between these two, or how we can divide these. An electrolyte is quite literally a substance that dissolves in water to give an electrically conductive solution. To give an electrically conductive solution. So for instance, when we drop sodium and chloride into water, this is classified as an electrolyte because the amount of current which was able to flow increased. Right? So the resistance decreased because we added an electrolyte into the solution. And again, that electrolyte is something that causes the solution to be electrically conductive. Conversely, we have non-electrolytes, or non-electrolytic, which are literally substances that dissolve in water to yield a non-conducting solution. Okay, non-conducting solutions are molecular substances. So these non-electrolytes, these are typically molecular substances. So in our example, we replaced the sodium chloride with sucrose, and we noticed that there wasn't any change, or there was a negligible change in the amount of current that was passing through that voltmeter. So typically these are molecular substances that are non-electrolytes. It is not to say that all molecular substances are non-electrolytes, but typically non-electrolytic solutions are molecular substances. One of the classic examples of a molecular substance that actually is an electrolyte is hydrochloric or hydrogen chloride. So if we have hydrogen chloride, which actually exists as a gas, and we drop it into water, we actually get aqueous. And again, remember that aqueous means in water or in solution. We get hydrogen ions and chlorine ions. And these actually are a conductive solution, or makes water more conductive, just because it dissolves readily in water to yield hydrogen ions and chlorine ions. So what we get, or what we come to, is this idea of solubility. And we get these solubility rules. Now, according to our chart, we can use these solubility rules to determine whether or not something will be soluble in water. So these solubility rules, it's a table that has been devised by chemists, and there are 8 rules, which you'll see in your chart, which can be used to determine whether or not something is soluble. So we have 3 examples. A, we have mercury chloride. We have potassium iodide. And lastly, lead to nitrate. We are asked to determine whether or not these are going to be soluble in water. Now, according to our chart, we'll take a look at part A first. According to Rule 3, so Rule 3 says that most compounds that contain chloride are soluble, however, or with the exception that mercury, or those chlorides that contain mercury, is listed as one of the exceptions to the rule. So it does not dissolve in water. So therefore we would say that mercury chloride, according to Rule 3, insoluble. And that's literally how we progress through these types of problems. We're asked to find whether or not they will be soluble. We look at the compound itself. So we look at what it applies to, and then we can determine whether or not it's insoluble or not. So taking a look at potassium iodide, we look at our chart. We say, okay, according to both Rule 1, so Rule 1, which says that group 1A compounds are soluble, and Rule 3, so Rule 1 and Rule 3, that most iodides are soluble, Ki is expected to be soluble. So, therefore, Ki is soluble in water. In a similar fashion, we look at lead to nitrate again. And looking at our chart, we see rule number 2 says that acetates and nitrates are soluble. They are soluble. Since there are no exceptions to this rule, lead nitrate then therefore should also be soluble in water.